Hey everyone. So here's Law of Cosines Day 2. I thought we could practice some Law of Cosines problems just to get warmed up. And then I wanted to look at two of the homework problems that traditionally give students some challenge, problems number 24 and 26. I'd like to introduce a new area formula. I know we had one with Law of Sines for side angle side, and now we get another one for side side side. This is one of the oldest area formulas when you have three sides of a triangle, but it's not a right triangle. And then also, I want to maybe think about doing a little review of law of sines problems. So let's start with a little practice for us. Here are the sides of a triangle, 2, 3, 4, and I'd like you to solve that triangle. So 2, 3, 4, and we'll call this A, B, and C. And if you want to try along at home, you should pause the video now, do the problem, and then turn it back on when you are all done. Okay, so pause now if you're trying it at home. I'm ready to keep trying though. So I'm going to find this one first. Cosine B equals 2 squared plus 3 squared minus 4 squared over 2 times 2 times 3. And when I do that, I get, hello little calculator, I get parentheses 4 plus 9 minus 16, negative 3 divided by 4 times 3 is 12. And so I get negative 1/4. But that's what cosine of b is, so I need to do the inverse cosine of that number. Oh, and I'm in radians because I was doing some graphing of trig functions. Okay, let's try again. Inverse cosine negative 0.25, and I get that this is 104.476 degrees. Okay, what about this one? So I know that cosine of C would be 4 squared plus 3 squared minus 2 squared over 2 times 4 times 3. So 16 plus 9 minus 4 divided by 8 times 3 is 24. And then inverse cosine of that. And I get that C is 28.955 degrees. And you could subtract these from 180 to find A. It wasn't that big a deal, so I'm just going to find cosine A as 4 squared plus 2 squared minus 3 squared over 2 times 4 times 2. So we've got 16 and 4 is 20. 20 minus 9 is 11 divided by 16. And if I do inverse cosine of that, I get 46.567. So if I add up all of these, plus 28.955 plus 104.476, then I get something just based on rounding error remarkably close to 180. And so there's my solved triangle. Those are the three angles. Okay, let's try another one. How about A equals 60 degrees, B equals 20, and C equals 30. So we've got two sides and the angle in between. You might want to pause the video now if you're going to try this on your own. This letter, by the way, in the glare of the lamps says C. Okay, pause if you're trying it on your own. I, however, do not need to pause because I'm just going to work the problem out. There's A, B is 20, and C is 30, and there's a big C. So we know that A squared equals 20 squared plus 30 squared minus 2 times 20 times 30 cosine of 60. So I get A squared is 400 plus 900 minus 600 times 2 is 1200, and the cosine of 60 is 1/2. So I have a squared equals 1300 minus 600 is 700, and so I know that a is the square root of 700. Square root of 700 is 26.456. Oh, 458. 458. Okay, so now I've got three sides. I could, of course, switch to law of sines at this point, but I don't find it that big a deal to use law of cosines with these three sides to find another angle. So I'll say cosine of b equals 20 squared plus, whoops, not if I'm finding b, it isn't. It's 30 squared plus 26.458 squared minus 20 squared over 2 times 30 times 26.458. Okay, so parentheses 30 squared plus 26.458 squared minus 20 squared, all of that in parentheses, divided by parentheses 2 times 30 times 26.458. Okay, that's what cosine is equal to, so if I do the inverse cosine of that, I get that this angle here is 40.893 degrees. So we've used up a little more than 100 degrees. 180 minus 60 minus the angle I just found is 79.107 degrees. Across from the biggest side is the biggest angle. Across from the second biggest angle is the second biggest side. And across from the smallest angle is the smallest side. So I feel pretty confident about that. Okay, let's move on. How about this one? A equals 58. Little a is 4.5, and little b is 12.8. So I've got 58 and 4.5 and 12.8. And this is big B, big C, little c. Okay, we solve that triangle and if you want, pause it now. So the first thing I notice here is I have an opposite side angle pair. This isn't law of cosines. This isn't side angle side or side side side. This is law of sines because I have the opposite side angle pair. So sine of 58 over 4.5 equals sine of b over 12.8. I have to use b because I know the side across from it. So then the sine of b will be 12.8 sine of 58 over 4.5. 12.8 divided by sine of 58, I'm sorry, not divided by, but times sine of 58 divided by 4.5. Now, I notice that that's supposed to be 2.412. Well, guess what? Sine will never be equal to a number bigger than 2. So this is no solution. Don't forget, no solution exists with law of sines. Okay. How about this one? A equals 25, B equals 80, C equals 60. All right. Will you please solve that triangle? Pause the video if you're working on your own. Got A, 25, B, 80, and C, 60. So if I find this angle first, I'll know that the cosine of B is 60 squared plus 25 squared minus 80 squared over 2 times 60 times 25. So we get 60 squared plus 25 squared minus 80 squared. And I want to divide that number by 2 times 60 times 25. And I get that cosine of b equals negative 0.725. And then when I do the inverse cosine of that, I get that b is 136.469 degrees. Okay, and how about we find c? Cosine of c equals 80 squared plus 25 squared minus 60 squared over 2 times 80 times 25. 80 squared plus 25 squared minus 60 squared divided by 2 times 80 times 25. Remember, when you're dividing, put all that stuff in parentheses. Oh, okay, and that's what cosine of c is, so if I do the inverse cosine of that, I get that c is 31.102 degrees. And then finally, I want to find angle A. Of course, I could subtract these two from 180, but I'm just going to confirm my answer by doing cosine A equals 80 squared plus 60 squared minus 25 squared over 2 times 80 times 60. Because if I made a mistake with one of these and I did the subtraction method, that's guaranteeing that this will be wrong as well. Okay, so I've got parentheses 80 squared plus 60 squared minus 25 squared, and I want to divide that by 2 times 80 times 60. Okay, and if I do the inverse cosine of that, I get this is 12.429 degrees. Let's add these up and see how close we got. That one plus 31.102 plus 136.469. And I get 180 degrees to 3 decimal places. So I feel good about these angles. Okay. How about this one? We've got A equals 58 degrees, B equals 11.4, and C equals, I'm sorry, this is mislabeled, this is little a, and this one is B, 12.8. So I've got big A is 58, little a is 11.4, and little b is 12.8. Okay, you might want to pause the video now and try the problem, and turn the video back on when you're done. I'm going to put my A over here, and 11.4, 12.8, big B, big C, little c. And again, I see this isn't going to be law of cosines because I don't have side angle side, and it's not law of cosines because I don't have side, 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 but I do have an opposite side angle pair, so it's law of sines. So the sine of 58 over 11.4 equals the sine of b over 12.8. Okay, so I'm going to find angle b as 12.8 sine of 58 divided by 11.4. 12.8 sine 58 divided by 11.4, and then do the inverse sine of that, and I get that this is 72.212 degrees. Okay, so I've got that one, and I still need to find these two pieces. But I remember that this is a law of sines problem. And one of the things that happens when people start doing law of sines problems is they forget to check for a second solution. So I'm going to check now for a second solution. So I know that b prime would be 180 minus b. So if I do 180 minus this angle that I just found, I get b prime equals 107.787 degrees. Is there room for a second solution with my given and my prime? Well, 58, 11.4, 12.8, but now we have B prime, big C prime, little c prime. And we just found that this was 107.787, and I'm wondering, is there enough room for a third angle? And I believe that when we subtract this B prime that we found, and then subtract the 58 degrees, lo and behold, we get 14.212 degrees. So there is a second solution, and so remember, we've got to check for that second solution, and I think the sooner you check for it, the more likely you are to be able to notice that there's supposed to be a second solution. Okay? Up here with this one, we've got 180 minus 58 minus 72.212, and so this one is 49.788 degrees. And now it's just a matter of doing a law of sines problem to find little c, and a law of sines problem to find little c prime. So let's set those up. We're going to have sine of 58 over 11.4 equals the sine of 49.788 over little c. So little c is 11.4 sine 49.788 divided by sine of 58. 11.4 sine of that answer divided by sine of 58. And I get 10.266. 10.266. Okay, and now for this one, how about 11.4 over sine of 58 equals little c prime over sine of 14.218. So little c prime then would be 11.4 sine of 14.218 divided by sine of 58. Let's take a look at what that'll be. 11.4 sine 14.218 divided by sine of 58. And I get 3.302. 3.302. Fabulous. So there's our solved triangles. Don't forget to check for two solutions. Okay, maybe at the end of the video we'll do a little more practice. But right now what I'd like to do is look at this other area problem that we talked about. This other area formula, an area formula that we use for for side, side, side. Remember, we said that we could find the area of a triangle using 1/2 base times height. But what happens if we don't have a right triangle, but instead we have something like a, b, little b, c, little c? Well, in this situation, we said then that area would be 1/2 AC sine b, or 1/2 AB sine c, or 1/2 BC sine A. This is called the side angle side approach for finding area, because notice the elements that are being used in the formula. There's a side and an angle and the side, and it's the angle that's in between the two sides. So here are our two sides, and this is the angle in between, our two sides and the angle in between. So there's our side angle side formula. But today I want to talk about an area formula. It's quite old. It's Heron's formula. The derivation is easier than the derivation for the law of cosines, but not as easy as the derivation for law of sines. The derivation is in the back of your book, and you might want to try it out if you're looking for a little challenge. But Heron's formula depends on something called S, the semi-perimeter. And so what's the semi-perimeter? Well, if we've got this triangle with sides A, B, and C, Heron says that the semi-perimeter is A plus B plus C, not divided by 3, divided by 2. That's why it's a semi-perimeter. And so he says that the area formula will be the square root of S, S minus A, S minus B, S minus C. And if you'd like to see how he came up with that, take a look at the derivation in the appendix. What I'd like to do is just sort of run through an example or two using Heron's formula with you. So let's take the side lengths of the problem we did earlier, where A was 2, B was 3, and C was 4. So what would our semi-perimeter be? Our semi-perimeter would be 2 plus 3 plus 4 divided by 2, and that's 4.5, because this is 5 plus 4 is 9 divided by 2. So then our area formula would be 4.5, 4.5 minus 2, 4.5 minus 3, and 4.5 minus 4. So, conveniently, I can pull out a calculator. Heron certainly didn't have this ability to use nifty graphing calculator like we do. Square root of 4.5, and then I want to times 4.5 minus 2, 4.5 minus 3, and 4.5 minus 4, and close parentheses. There's a lot of parentheses going on here, and you're welcome to tidy this up. Let's just confirm what we've got. Square root 4.5, 4.5 minus 2 is in parentheses, 4.5 minus 3 is in parentheses, and 4.5 minus 4 is in parentheses, and then I close out the square root parentheses. And I get that the area is 2.905 square units. Okay, we didn't talk about how long what units these sides had, so that's all we've got. Okay, so what we had to do was find that semi-perimeter by adding up the sides and not dividing by 3, which is a really common mistake, but dividing by 2 because it's a semi-perimeter. Semi-annually is twice a year. Semester, you got 2 of them a year. So semi-perimeter, you're dividing by 2. And then we take Heron's formula, which is S times S minus A times S minus B times S minus C, and we take the square root of that. Okay, so here's one for you to try. Please find the area of this triangle. Where's our triangle? There it is. A equals 25, B equals 80, C equals 60. You might want to pause this video now and give it a try. Okay, so the semi-perimeter is 25 plus 80 plus 60 over 2, which is 165 over 2, or 82.5. So the area formula then is the square root of 82.5. 82.5 minus 25, 82.5 minus 80, and 82.5 minus 60. Okay, 25 plus 80 plus 60 divided by 2 is indeed 82.5. Store that in x because I'm going to be using it a lot. Square root of x times parentheses x minus 25, close parentheses, open parentheses, x minus 80, close parentheses, open parentheses, x minus 60, close two parentheses. And I end up with the area being 516.5 0.62 square units. Okie dokie, there's Heron's formula. So what about the area of this triangle? Big A equals 58 degrees, little a is 11.4, and little b is 12.8. Okay, please find the area of this triangle. You might want to pause the video now and give that a try. So here's what I notice when I start this problem. 58 degrees, 11.4, 12.8. And this would be big B, big C, little c, and big A. I don't have side, side, side is what I notice, and so I can't use Heron's formula. I can't even use our method of side angle side. Side angle, I don't have this side yet. So I'm going to have to use law of sines here first to get anywhere with the problem. So how about the sine of 58 over 11.4 equals the sine of b over 12.8. Okay, so now we've got 12.8 sine of 58 over 11.4 is the sine of b. And so when we did this problem earlier, 12.8 sine of 58 divided by 11.4, and do the inverse sine of that number, I get b equals 72.212 degrees. But this was the problem where we also had a b prime. And I'm wondering, do you think that matters? Do you think we'll get a different area for our two different triangles? 107 and 787. 788, sorry, degrees. Okay, so we know this one is 72.212 degrees. And I still don't have enough information for Heron's formula, and I still don't have enough information for that side angle side approach. I'm going to need to find one more piece of information. So I can subtract these two angles from 180 to get that. And so I'll have 180 minus 72.212 minus 58, and I get 49.788 degrees. And now I'm ready to do a side angle side approach here. That would be 1/2 12.8 11.4 times the sine of 49.788. All right, let's see what we get. 0.5 times 12.8 times 11.4 times the sine of 49.788. And I get 55.717 units squared. And that was working with this triangle. But what about this other triangle, where this is 107.788 degrees, and this is 58, and 11.4, and 12.8. So let's find our big C prime now. 180 minus 58 minus 107.788, and I end up with 14.212 degrees. And now if I use that side angle side approach to finding the area of this triangle, that would look like 1/2 12.8 11.4 and sine of 14.212. Is it going to work? Is it going to be the same? Let's see. 0.5 times 12.8 times 11.4 times sine of 14.212, and lo and behold, we get 1/2 side angle. Great. 17.912. Hey, that's not the same. So when we have two solutions, we get two different areas sometimes. And I would need to check both. if this were honors trig class, I'd put a problem like that on the test. But for regular trig class, no, nothing that hard. Okay, so those are the reviews that I wanted to do so far. Maybe we should end with one more two-triangle problem, but I actually wanted to look at homework questions from assignment 59. I'm sorry, assignment 60. Problem number 24 dealt with this parallelogram where we had A, B, this angle here was phi, this angle here was theta, and then they drew in the diagonals. This one was D, and this one was C. So when they give us a C value or a D value, it's not just this piece, it's the whole diagonal. And we talked about in the video for assignment 59 that the diagonals of a parallelogram bisect each other. So in our problem, where A is 40, B is 60, and D is 80, let's put what we know in. I'm going to take out a lot of the rest of this visual noise. Okay, so this whole thing is 80, and this is 40, and this is 60. Now, the nice thing about this is that I can find this angle pretty easily. This was theta, and we know that the cosine of theta is going to be 40 squared plus 60 squared minus 80 squared over 2 times 40 times 60. So let's find out how big theta is. 40 squared plus 60 squared minus 80 squared, and I want to divide that by 80 times 60. And I take the inverse cosine there, and I get that theta equals 104.478 degrees. That's how big this angle is. Remember, we also need to find phi. And we know that theta and phi, same side interior or adjacent interior angles, they're going to be supplementary. So all I have to do is 180 minus theta to get phi. If I find one angle, finding the other one is pretty straightforward. 75.2522 degrees. Okay, those are the two angles. We've got three sides, but we still need to find this diagonal here. This diagonal here, C. We know this is 40 over here. Well, now what? Well, some students want to say that the diagonals bisect these angles. And let's see if I can draw a picture for you that convinces you one way or the other about that. Is this angle the same as that angle? Yeah, no, they don't look at all the same. So, no, that's not a property of parallelograms, so I can't say that if I take theta and divide it by 2, I know how big that is. I'm going to have to do this some other way. And conveniently, the other way is, remember how we said that opposite angles were congruent. So if this one is 75.522, then this one is also 75.522 degrees. And now I've got side, angle, side, and I can use law of cosines to find C. We would say C squared equals 60 squared plus 40 squared minus 2 times 40 times 60 times the cosine of 75.522. All right, let's see what that turns out to be. We've got 60 squared plus 40 squared minus 2 times 40 times 60 times the cosine of 75.522. And don't forget that's what C squared is. We still need to take the square root of that answer. And so I get that C equals 63.245. And so that's all four sides and both angles that we were asked to find in number 24. 26 is a little more involved. In 26, we're still talking about this parallelogram with those sides labeled the same way, except this is 25. This whole diagonal is 50, and I'm going to use a color for D. D is this one, and D is 35. So, yeah, I've got sides, but I don't see three sides of a triangle, and I certainly don't see any angles. And so my recommendation is that you remember that the diagonals of a parallelogram bisect each other. So even though this whole diagonal is 50, I know that this is 25 and this is 25. And even though this whole diagonal is 35, I know that this is 17.5 and this is 17.5. And now when I look at it, I see, oh, I've got side, side, side here. Or, yeah, I've got side, side, side there. So let's see what we can do with side, side, side. The first thing we can do is we can find that angle. And I don't have a name for it. Let's call it x. So we know that the cosine of x will be 17.5 squared plus 25 squared minus 25 squared over 2 times 17.5 times 25. Well, you know, conveniently those cancel out, so the numerator is just 17.5 squared, and I want to divide that by 2 times 17.5 times 25. Okay, so that's our cosine value. If we do the inverse cosine of that, I get that x equals 69.513 degrees. So that's 69 degrees. How big is this angle next to it? Well, 180 minus the angle I just found, and we'll call that one y. Y is 110.487 degrees. Now, I want to know this one because now I'm looking at a triangle, this triangle, where I have 25, 17.5, and 110.487 degrees. And I'm looking for A. So I know that A squared will be 17.5 squared plus 25 squared minus 2 times 17.5 times 25 cosine of our 110.487 degree angle. Okay, let's compute A then. 17.5 squared plus 25 squared minus 2 times 25 times 17.5 times the cosine of that angle. And don't forget that's what A squared is, so we want the square root of that number. And I get that A is 35.178. A is 35.178. Okay, well, what do we still need to find? We need to find theta and phi. Well, I see here this triangle, and I know this side is 50, and this one is 35.178, and this one is 25, and there's my theta. So cosine of theta will be 35.178 squared plus 25 squared minus 50 squared over 2 times 35.178 times 25. So let's see what that is. I'm going to store this side in x, and I'm going to say x squared plus 25 squared minus 50 squared, and then I'm going to divide that by 2x times 25, and I get this, but that's what cosine of theta is. Don't forget to do the inverse cosine. and I get theta is 111.250 degrees. And remember, theta and phi in this parallelogram are supplementary, so I don't have to repeat the process with this triangle, 25, phi, 35. I could if I wanted to, but I can just subtract this one from 180 to get, to get my answer. And so I get 69.749. I guess that's gonna round up to 750 degrees. And there we go. There's another approach to this problem where after you find these, after you split this up, that you find this angle using law of cosines on this triangle, and then you find, what was the other one? I want to find this one. Boom, 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 boom. I know that these are equal. I know that these are equal. Yeah, so there's this approach where I can find this angle. I can find these pieces and add these pieces together. But I can find this one pretty straightforward with these three. And I can find this one up here because these are congruent, but that's not helpful to me. I'm trying to figure out a way to find this one, and this one is alternate interior with that one. And I know that this is 17.5, and I've got this. So I have enough information, but I still have to find that side first. I think that that only using the diagonals to help you find A is much smarter or much more efficient. I don't want to say smarter, because I think it's cool when you can see that. But it's certainly more efficient to move from there back to something like this and say, okay, now I've got this triangle and I want to find phi, or the way we did it, I've got this triangle and I want to find theta. Okay, so those were the two questions from the homework. And I think I just wanted to look at two more problems with you. One in honor of baseball, because it is the spring, even though we're inside. Here's a baseball diamond has 4 bases forming a square. Roughly speaking. And the bases are 90 feet apart. And we have the pitcher's mound is here, 60.5 feet from home. Why isn't it here, halfway across down that diagonal? And the answer is because the play from first to third would pass through the head of the pitcher, and pitchers are a little more valuable than that. So we scooch that forward and save the pitcher's arm a little bit. Okay, so what we're asked to find here is what's the distance from the pitcher's mound to each of the other 3 bases. So we want to find distance 1, distance 2, and distance 3. Now, I'm going to argue that, that these two triangles are congruent, and therefore distance 1 and distance 2 are the same. It's the same distance whether we throw to first or whether we throw to, in fact, I'm going to call that D3. It's the distance to third base, as opposed to D2. This is the distance up to second base. First, second, and third. Okay, so what do we know? We know this is 60.5. Anything else? Well, here's something we do know. While we don't know in a parallelogram, we do know in a square and in a rhombus that these angles are equal. And so this diagonal cuts this angle into two equal pieces, and so that's 45 degrees. And this is 45 degrees. And remember I said that this distance would be the same as this because these triangles are congruent. And look, we've got side, angle, side, and the same side, the same angle, the same side. So the distance for one will be the distance for the other. That's not going to be true for D2. We'll find that in a bit, but let's first start by finding D1. I've got, do I have an opposite side angle pair? No. But I do have side angle side, so I can use law of cosines and say that D1 squared will be 60.5 squared plus 90 squared minus 2 times 60.5 times 90 cosine 45. Okay, so 60.5 squared plus 90 squared minus 2 times 60 times, 2 times 60.5 times 90 times the cosine of 45. And if I take the square root of that, I get that the distance from pitcher's mound to first or third is approximately 63.717 feet. Okay, but now what about D2? Well, that's a different angle. And, or I should say that angle is still 45. I don't know this, but I do now know that this one is 63.717 feet. I have an opposite side angle pair there, and one more side, so I could find that angle, but I'm looking for this. So a long way to do this problem would be the sine of 45 over 63.717 equals the sine of the pitcher's mound, that's this angle P here, over 90. So 90 sine 45 divided by 63.717. And don't forget to do the inverse sine of that answer. And we get that the pitcher's mound angle, this angle in here, and it's feeling a little cramped in there for me. I'm going to draw it big, 87.176 degrees. This is 63.717. This is 90. This is 45. And we're looking for D2. Okay, so if I find this angle, subtracting these from 180, I can then use law of sines to find D2. So 180 minus the angle we just found, minus that 45 degree angle, gives me 47.824 degrees here. And then I can build one more law of sines to say sine of 45 over 63.717 equals sine of 47.824 over d sub 2. So d sub 2 then will be 63.717 sine of 47.824 all over sine of 45. Let's see what that turns out to be. 63.717 sine 47.824, close parentheses, divide by the sine of 45, and I get 66.789, 66.789 feet. But there's an easier way to find D2, especially since we already know the distance to home. And that is to use something we learned back, at least in geometry, where this is 90, 90, right angle. This is a 45, 45, 90. And what we learned in geometry class is that if we multiply the leg of a 45, 45, 90 by root 2, we get the hypotenuse. So this whole distance, this whole diagonal from second to home is 90 root 2. And we know this part of it. So if we do 90 square root of 2 minus 60.5, we end up with 66.7779. Did I copy that wrong before? I did copy that wrong before. 779. And we get that same answer by doing 90 root 2 minus the pitching distance. Okay, I think that's a lot faster, but many students don't see or recognize the 45-45-90 triangle and have to go the long way. All right, well, I think that was a nice reminder of law of sines and definitely some practice with law of cosines. And that's all the material that shows up on the next assessment. I do want to give you some law of sine and law of cosines word problems in a review assignment. That'll be what we look at next. And then I'll offer people who want the opportunity to try out the quiz that we have on non-right triangles. But for today, that's all we've got. Hope you have a great day, everyone. Take care.